Right, with this problem, I want to look at again flow through a pipe or a tube. In this case, it is a very, very long tube with a length of 150 meters, and the tube diameter, inner tube diameter, is 10 millimeters. It is a thin-walled tube, and it is made from commercial steel. Now, normally a tube with this diameter and length you will not get in commercial steel. It will normally be a hard-drawn or a soft-drawn tube. Usually you will not get them in these types of lengths, but there's a very specific principle that I want to show, and that is why I've selected these dimensions. We have water flowing through the tube, so it's water, and the inlet conditions, inlet temperature is 20 degrees Celsius, and the velocity of the water is 1 meters per second, and the inlet pressure is 500 kilopascals. Now this tube is being heated at a constant heat flux. So typically an electrical wire is coiled around this tube, and we've got a current flowing through it, and the heating is with a heat flux of 5.5 kilowatts, 5.5 kilowatts per square meters. And we have to determine the outlet temperature of the water. We have to determine the surface temperature at the outlet, the surface temperature of the tube. We have to calculate the pressure drop, and then also the fluid power, the pumping power required to pump the water through this tube. Now, it is very important that you first look at my lectures 01 to 05 of 2015 on internal forced convection before you try to do this problem. The purpose of this problem is not only the calculation of these values, but there are two things that I want to concentrate on. The one is that it is a constant heat flux problem, and the other one is the influence of the properties in terms of the selection, at what temperature it is being selected if you want to do the calculations. So with these types of problems, with internal forced convection, if you look at the lectures, you will see that there are two types of internal forced convection problems. The one type is where the surface temperature is constant, and the other type is where there's a constant heat flux. Now, with this, we have a constant heat flux. Now, with a constant heat flux problem, if we look at the fluid temperature that is being heated or cooled, and that is the inlet temperature of 20, because the heat flux is constant, so for every 1 meter or 1 millimeter, we put in the same amount of heat. And for that reason, there will be a linear increase in the fluid temperature over the tube length. So this is the temperature, and that is the length, and this is 150 meters. So the temperature is going to increase linearly, and that is then TE, the outlet temperature that we have to determine. Now the surface temperature will have the following characteristics. It will have a first part through which the flow will be developing, and during the developing flow, the boundary layer will increase in thickness, so it will start to be very, very thin. If the boundary layer is very thin, then the heat transfer coefficient is very high, and then it will decrease, and typically that is what is going to happen when the flow develops. So this is fully developed flow, and this is the developing part. Developing. So the developing flow part and the fully developed flow part. Now, as soon as the flow is fully developed, then the heat transfer coefficient will be a constant, and the result will be that we will have a constant delta T between the fluid temperature and the wall. So this is the surface temperature, and let's call that TSE. That would be the surface temperature at the outlet. So as the fluid temperature increases, the wall temperature is also going to increase. The first part is the developing part until it's fully developed. After that, we will have a constant temperature increase. So that is in general the characteristics of these types of problems. Now, when we have these types of problems, there's not a specific recipe that we have to follow, but the things which are normally very important to calculate would of course be the Reynolds number, because the Reynolds number is going to tell us if the flow is laminar or turbulent. Based on that, we can try to get the heat transfer coefficient, the Nusselt number. Or to get the heat transfer coefficient, we first need to get the Nusselt number. And the other things which are normally very, very handy to have and that we use all the time, it would be the mass flow rate. It would be typically the velocity, which has been given in this case, the cross-sectional area through which the flow occurs, as well as the surface area through which the heating occurs. Now, something that students find very, very difficult is the following. So when we start with these types of calculations, we need certain fluid properties. And the fluid properties are normally typically the density, it would be the Cp value, it would be the thermal conductivity, it would be the viscosity, and it would be the Prandtl number. Typically, with calculation of the Reynolds number, we would need the density and the thermal conductivity. With the heat transfer rate, we need the Cp. With the Reynolds number, we typically need the density and the viscosity. With the heat transfer rate, we need the Cp value. With the Nusselt number, we need the K value, and also with the calculation of the Nusselt number, also the Prandtl number. However, the question is, where do we get these values? Obviously, it is water, so we can go and look at tables which are available on the internet or in textbooks for water. But if you look at the properties of water, you will see that these properties are a function of temperature. So you have to go and make a selection at a certain temperature. Now, what we normally do is we take it at the bulk temperature, and the bulk temperature would be the average of the inlet temperature and the outlet temperature divided by 2. So the bulk temperature is just the average between this temperature and that temperature. Now, the problem that we have in this case is we've got the inlet temperature, but we do not have the outlet temperature. It is one of the things that has been asked that we should determine. So the question is now, what bulk temperature do we choose if we cannot actually calculate it? Well, what you can do is you can just make an assumption. Now, again, now the question is, what are you going to assume for the outlet temperature or the bulk temperature? If you look at this problem, they say that the water has been heated, so they do not say that steam is being produced. So you can assume that this temperature most probably would not be higher than 100. So if you would assume it is 100 as an extreme, then you will have 100 plus 20 divided by 2, and that would give you a bulk temperature of 60 degrees Celsius. And that is what I would typically maybe do, or I would choose 50 or 40 or something like that. Some people choose typically this inlet temperature of 20, and then they would go and get the bulk properties there. And this is something that students find very difficult to figure out which bulk temperature they should choose. So what I'm specifically going to try to show you with this problem is that it is not really that important. What I'm actually going to do, as a matter of fact, I'm going to choose a bulk temperature which is a silly one, which is 5 degrees Celsius. We can see it is totally out of range. I mean, if we have an inlet temperature of 20 and the water is being heated, then obviously the water cannot ever get to 5 degrees Celsius. But just to show the principle, so at 5 degrees Celsius, I have looked up the values for the density, which is 1000 kilograms per cubic meter, the Cp value, which is equal to 4195 joules per kilogram Kelvin, the thermal conductivity, which is equal to 0.558 watts per meter Kelvin, the viscosity, which is equal to 0.001517 kilograms meters per second, and the Prandtl number, which is equal to 11.41. So those are the properties at 5 degrees Celsius, which is not really a good assumption that anybody should make. But I just want to show you the principle. So this whole problem is about two things which are important here. The fact that it is a constant heat flux problem, and secondly of how do we handle the properties and what will the influence be of a poor selection of the properties on the problem. Right. Now, the other thing that is always handy to have is to calculate the cross-sectional area through which the flow occurs, AC. So if that is the tube with its diameter of 10 millimeters, we want to know what is that area there. So that is the cross-sectional area. I'm going to make it in blue here to show you it is that area there. Okay. So that's a cross-sectional area. The cross-sectional area is very easy to calculate. It is equal to pi divided by 4 multiplied by the tube diameter square. And if you can calculate it, then it is equal to 0.40785 square meters. So that's a cross-sectional area through which the water will flow. The other area which is very important is the outside diameter, or the area through which the heat transfer occurs. And that would be that area there. Okay. Now, we have, of course, the area. If we look at the tube, then it will have a certain tube thickness, like that. Okay. And the tube diameter, which has been given as 10 millimeters, or the inner tube diameter as 10, it has also been said that this wall thickness is very, very thin. And if that is the case, then this surface area and that surface area would be the same. So the surface area through which the heat transfer will occur will be the perimeter multiplied by the length of the tube. The perimeter is pi multiplied by the diameter multiplied by the length. So it is pi multiplied by 0.010 multiplied by the length, which is 150. And that would give us a surface area of 4.721 square meters. Right. We do not have the mass flow rate, so let's just also calculate the mass flow rate. So the mass flow rate is equal to rho multiplied by the cross-sectional area multiplied by the velocity. The density is 1,000. The cross-sectional area we've calculated as 0.40785 square meters. And the velocity of the water is 1 meters per second. So the mass flow rate can then be calculated as 0.07857 kilograms per second. Right. So there we've got the cross-sectional area now, we've got the surface area, and we've got the mass flow rate. Let's calculate the Reynolds number, because the Reynolds number is going to tell us if the flow is laminar or turbulent, and that is very important. So the Reynolds number is equal to rho Vd divided by the viscosity. The density is equal, rho is 1,000. The velocity is 1, and the tube diameter is 10 millimeters. And the fluid velocity at this temperature of 5 degrees Celsius that we've selected, which is a silly temperature, is equal to 0.001517, and that gives us a Reynolds number then of 6,593. And this Reynolds number is not fully turbulent. Normally, fully turbulent flow would be at a 10,000 and higher, but the flow changes from laminar to turbulent in a round circular tube at about 2,100 to 2,300. Between 2,300 and 10,000, it is a little bit still in the transition flow regime, but it is difficult to say. But in this course, what we're going to do is, if the Reynolds number is larger than about 2,100 to 2,300, we're going to assume the flow is turbulent. So let's assume that the flow is turbulent. Right. Now, if the flow is turbulent, then we know two things which are very important. The one is that LH would be 10 times the tube diameter. Now, what is LH? LH is how long it will take before the flow is hydrodynamically fully developed. So that would be 10 times the diameter, which is 10 millimeters, and that is 0.1 meters, so that is 100 millimeters. Right. Now, if schematically, okay, and let's also, while we're here, calculate LT. Again, because the flow is turbulent, it would be 10 times D, and again, that would be 100 millimeters. So what does that mean? It means that on this whole tube length that we have, in 100 millimeters from the inlet, 100 millimeters, the flow would be fully developed, like a plug type of flow for turbulent flow, and also thermally, it will also be fully developed. So that is in that 100 millimeters. So if we look at this whole length of the tube, which is 150 meters, it would mean that this part is negligible. So if we go back to the sketch, it would mean that for this specific case, we have something like that. Okay. Okay. So it means that we can make the assumption that the heat transfer coefficient is actually constant throughout the tube length. The flow is fully developed. So the assumption that we make is the flow is fully developed. Now, if it was the case that the flow is fully developed only here, then it would mean that we need the correct equations that can give us the heat transfer coefficient while the flow is in the developing flow part for turbulent flow. It's not in most textbooks, but they are available in literature. So you can go and get them there. So now that we know that the flow is fully developed, we can go and calculate the heat transfer coefficient. But something that we could have done already is something very important, and that is we can actually go and calculate the heat transfer or the outlet temperature. Now the outlet temperature we can calculate by saying that the heat transfer rate is equal to the mass flow rate through the tube multiplied by Cp multiplied by the outlet temperature minus the inlet temperature. Let's just go back to this graph. So the heat transfer rate, so we are heating this fluid at a constant heat flux. Temperature increases linearly. So the heat transfer rate is equal to the mass flow rate, the Cp multiplied by the temperature difference. Now, we have the inlet temperature, we've got the mass flow rate, we've got the Cp. We do not have the heat transfer rate, but we've got the heat flux. The heat flux has been given, and the heat flux is equal to the heat transfer rate divided by the surface area through which the heat transfer occurs. And so and this has been given, the heat flux has been given as 5.5 kilowatts, so it's 5.5 multiplied by 10 to the 3 is equal to the heat transfer rate divided by the surface area, and the surface area is equal to 4.712. So therefore, the heat transfer rate is equal to 25,918 watts, or as an engineering answer, about 25.9 kilowatts, or about 26 kilowatts of heat that will occur. So now that we've got the heat transfer rate, we can go back to this equation. The heat transfer rate is equal to the mass flow rate Cp multiplied by the outlet temperature minus the inlet temperature. The heat transfer rate we've determined as 25,918 is equal to the mass flow rate, and now you can see why we've calculated the mass flow rate is equal to 0.07857 multiplied by Cp, which is equal to 4195, multiplied by the outlet temperature that we want to determine minus the inlet temperature, which is 20. So from this we can calculate the outlet temperature as 98.62 degrees Celsius. So if the pressure is equal to close to atmospheric, then it might be that the water starts to boil. Now, this is specifically the reason why I've selected this tube length so long, because I really wanted a huge temperature increase from the inlet to the outlet. So this outlet temperature we have determined now is equal to 98.62 degrees Celsius. There it is. Right. Now, let's go back to the calculation of the heat transfer coefficient. The heat transfer coefficient I'm going to calculate from the Dittus-Boelter equation. And the Dittus-Boelter equation says the Nusselt number is equal to 0.023 multiplied by the Reynolds number to the 0.8 multiplied by Prandtl to the n, where n is equal to 0.4 if we have heating, and n is equal to 0.3 if we have cooling. Now, why did I select the Dittus-Boelter equation? There's in most textbooks, there's a large number of equations that are available, like also equations like the Glinsky and the Petkov equations. The reason for that is just that this is the simplest one and the easiest one to calculate. But if you want to be very accurate, then you need to go to the Glinsky equation, for example. That would be better. So for this specific case now, we can calculate the Nusselt number as equal to 0.023 multiplied by the Reynolds number, which is 6593 to the 0.8, and the Prandtl number is 11.41, and n would be 0.4. Why 0.4? Because the fluid is being heated. So these values is for the fluid on the inside in terms of the internal forced convection. You need to do the selection according to that. So the Nusselt number, if we can calculate the Nusselt number now, then it would be equal to 69.17. Right. Now that we've got the Nusselt number, we can calculate the heat transfer coefficient, because the Nusselt number is equal to the heat transfer coefficient multiplied by the tube diameter divided by K. The Nusselt number is 69.17. It's equal to the heat transfer coefficient multiplied by the tube diameter, which is 10 millimeters, divided by the thermal conductivity of the fluid, which is equal to 0.558, and that will give us a heat transfer coefficient of 3,860 watts per square meter degrees Celsius. Right. Now that we've got this heat transfer coefficient, we can go back to the sketch and to the theory that we've already done on it. We know that, as I've said, that this delta T is now going to be a constant. We've made the assumption that the heat transfer coefficient is a constant right through the tube, because the flow is fully developed. And for that reason, it is very easy now to say, well, the heat transfer rate again is equal to the heat transfer coefficient multiplied by the surface area multiplied by the wall temperature minus the fluid temperature. So with calculation of the heat transfer coefficient, we normally have two choices. We can use the heat transfer rate as equal to the mass flow rate, the Cp, multiplied by the delta T of the fluid, or we can look at the heat transfer rate and say it is equal to the heat transfer coefficient multiplied by the area. I'm going to the sketch now, multiplied by the wall temperature minus the fluid temperature. So T wall minus T fluid. And we can write it as also as the heat flux. If we want to, we can write it also as the heat flux is equal to the heat transfer rate divided by the surface area. So I take this equation, I just divide it by the surface area, is then equal to the heat transfer coefficient. And I'm specifically now would like to look at this delta T here, because we have been asked to calculate that temperature TSE. So that is the heat transfer coefficient. The wall temperature there would be TSE, and the fluid temperature there it is. We've got the fluid temperature, we have already solved it. It's equal to TE. So write it like that. So now we can say that the heat flux is equal to 5.5 kilowatts. It's equal to the heat transfer coefficient, which is equal to 3,860 multiplied by the surface temperature at the outlet minus the fluid inlet temperature. Sorry, not TE, obviously 98.62. I just want to go back. So the heat flux, again on this sketch, the heat flux is equal to the heat transfer coefficient multiplied by TSE minus TE. So the heat flux is 5.5 kilowatts, the heat transfer coefficient is 3,860, TSE is that temperature there, TSE minus TE, TSE minus TE, and TE is then the fluid outlet temperature is 98.62, and now we can solve the surface temperature at the outlet is 100 degrees Celsius. Right. Now, we have also been asked to calculate the pressure drop. So if we just go back to what has been asked, we've been asked to calculate the outlet temperature, the surface temperature, and now we have to calculate the pressure drop and the fluid power to the fluid. And we can do that from getting the friction factor as a function of Reynolds number from the Moody chart. And the Moody chart would have this straight line. It's a log scale for laminar flow. There's where the flow changes from laminar to turbulent. And then for smooth tube, we will have a smooth tube means that epsilon divided by d. Epsilon is the surface roughness, internal surface roughness, divided by the tube diameter is equal to 0. So from this chart, we can get the friction factor. Now this is for a smooth tube, but in our case we've got a commercial steel tube. So we need to get the epsilon divided by d for our specific case. And the question is now, what is the surface roughness? Now, if you go and look at the literature, typically you can get the values on a Moody chart. And sometimes it is given on it, or you have to go and get it in tables, or you can go and get it from the manufacturer. But typically for a commercial steel tube, the surface roughness is equal to 0.045 millimeters. So it is 0.045 millimeters, so 0.045 multiplied by 10 to the minus 3, divided by the tube diameter, which is 10 millimeters, and that would give us a surface roughness of 0.0045, like that. So now, if we use the Moody chart and we go and look at the Reynolds number that we've calculated, which is equal to, where is it now, 6,6593, like there, then we can go and get the friction factor from here, and it would be approximately 0.03. So you can go and do it directly from there, or what you can do is you can use any of many equations, some more accurate than others, some more easier to solve than others. What I did is I've used the Lalande equation also to calculate it with, the Lalande equation, which is also in the textbook of Sengel and Gujar. The Lalande equation is 1 divided by the square root of the friction factor is equal to the minus 1.8 times the log of 6.9 divided by the Reynolds number plus epsilon divided by d divided by 3.7, everything to the power of 1.11, like that. And that is then the Lalande equation. And you can see the Lalande equation takes into consideration the surface roughness. And if you put it in here, you can actually go and solve the friction factor as equal to 0.0397. So you can see you can solve it much more accurately than you'll be able to see it on a Moody chart. So if you actually can do it very, very well and you've got very good eyes, and then maybe you can go and get it so accurate so that the friction factor there is equal to 0.0397. Here is also a Moody chart that I've got from the internet. You can just see it. I'm just going to paste it here, typically like that. So here there's much more detail. I'm sure it would be very difficult for you to see it on your screen. But typically here again, you've got the friction factor as a function of Reynolds number. The Reynolds number is then equal to 6,500, which is approximately, it's very difficult to see, it's somewhere there, 6,500. And here you've got all the different surface roughnesses. There is 0.004, so it is that line there. So where the two crosses there, you can go and get it there, and from there you can go and get the friction factor there. And take note, in this case it is 10 to the minus 3, but in any case you'll see the principle. So go and look at the Moody chart and you can go and see that you can go and get the friction factor as approximately 0.0397. It is always a good thing that if you do the calculation, just go to the graph and see that it is approximately correct, because it's very easy to make a silly calculation error when you calculate these things. But in any case, now that we've got the friction factor, we can calculate the pressure drop. The pressure drop is equal to the friction factor multiplied by L of D multiplied by rho V squared divided by 2. So the friction factor we've calculated as 0.0397. The length of the tube is 150 divided by the tube diameter is 10. The density is 1000. The velocity is 1, so it is 1 squared divided by 2. And from here we can calculate the pressure drop as 297,850 Pascal. So that is about 298 kilopascals. Right, now the inlet pressure, if I can come back to the problem, remember the inlet pressure has been given as 500. So if this is the inlet pressure is 500 and we've got a pressure drop of 298, we can calculate the outlet pressure is going to be equal to 500 kilopascals minus 297,850, and that would give us an outlet pressure of about 202 kilopascals. Okay, so with this pressure of 202 kilopascals and this outlet temperature that we've calculated of 98, we can be sure that we will not have any boiling of the water as it is being heated. Now the other thing that we need to calculate is the fluid power, and that we can calculate normally with the volume flow rate multiplied by delta P. But the mass flow rate, remember, is equal to the density multiplied by the volume flow rate. So we can write this then also as the volume flow rate, which is the mass flow rate divided by the density multiplied by delta P. And now we can calculate it. The mass flow rate we have determined is equal to 0.07857 divided by 1000 multiplied by delta P, which is then 202 kilopascals, and it gives us then 23.39 watts. So it is very small, and the reason for that is that it's a very small diameter tube. The velocity is 1 meters per second, so the mass flow rate is not that high. So there is the fluid power. Right, now we've calculated everything that was asked from us. Let's just go back in terms of what was asked from us. We were asked to calculate the outlet temperature, the surface temperature, the pressure drop, and the fluid power, and we've done everything in that regard. Now, the question that we have to ask ourselves is this correct? And correct specifically in terms of my selection of the inlet temperature. Not the inlet temperature, the bulk temperature. We've got an inlet temperature of 20, we've got an outlet temperature of 98.62. So now we can actually go and calculate the bulk temperature much more accurately. The bulk temperature, again, the inlet temperature plus the outlet temperature divided by 2. The inlet temperature is 20, the outlet temperature is 98.62 divided by 2, and that would then give us a new bulk temperature of 59.31 degrees Celsius. Okay, so that's a new bulk temperature. Okay. So what we need to do now is, now we have a much more accurate bulk temperature because we have the outlet temperature, and let's just go and look at what happens with the properties. If we now look at the properties, then we will see that at this temperature the properties changes to the following values. The density is now going to change to 984, so it is not that much. The CP value is going to change to 4180, also not that much. Thermal conductivity equal to 0.6407, so it increases with about 10%. But the viscosity changes significantly. It changes to 0.004717, and the Prandtl number changes to 3.078. So we can see that specifically the viscosity and the Prandtl number changed significantly. And for that reason, we need to use these values now and recalculate everything. If we do that, then the Reynolds number is now going to change to our new Reynolds number. If you can do the calculations, it is going to change to 20,860. So again, it is turbulent, but it is now fully turbulent. Previously our Reynolds number was 6,500. So it increased with about a factor of 3, the Reynolds number. So that is quite a lot. If we go and calculate the outlet temperature, new outlet temperature is going to be about 100.3. So fortunately, because the pressure is not atmospheric, it is more than 202 kilopascals at the outlet temperature, the fluid will not be boiling. We can go and calculate the Nusselt number. The Nusselt number is going to change to 102.9. The heat transfer coefficient, new heat transfer coefficient, is going to change to 6,594 watts per meter degree Celsius. The surface temperature at the outlet is going to change to 101.1 degrees Celsius. The friction factor is going to change to 0.0334. And the pressure drop is going to change to 246 kilopascals. And the fluid power is going to change to 19.36. Right, so you will see that there are changes, fortunately not that much. And if we now go and calculate, now that we've done the iteration again, we've calculated the new outlet temperature now of 100.3. We can go and calculate the new bulk temperature again as 20 plus 100.3 divided by 2, and that is equal to 60.11. Okay. And again, if you want to, you can go and repeat the calculation again. So if you go and repeat the calculation for a third time, okay, so for a third time, now with this new bulk temperature, so the first bulk temperature, the first selection was 5. We did go through the calculation. Now we've calculated the outlet temperature. We get a bulk temperature then of 59.31. Go through the calculation, then it is going to be 60.11. And if you're going to do it again, it is going to be, it converges to 60.13. So you'll see that with these types of problems, so the thing that is very important that I want to show you is the effect of your selection of your bulk temperature. So you will see that even although it was a very irrational decision, if you do the calculation and if you iterate it once, it really converges very, very quickly to the correct answer. So with that, I would like to end this lecture, except for one other thing that I want to do, and that is just to show you on a TS diagram what is happening with the pressures and the temperatures. So that is a TS diagram. We know typically that for a pressure of atmospheric, which is 101.133 kilopascals, then water will boil at 100 degrees Celsius. Okay. Now in this case, we had water at 500 degrees Celsius, 500 kPa, and if you go and look at the saturation temperature of 500 kilopascals, it would be 152. Okay. And the other temperature other pressure that is important is the outlet pressure. The outlet pressure, which is 202 kilopascals. So let's put it in there, like that. Okay. Now what is very important to realize is that this is not according to scale. These lines are very, very close to each other. The angle here is very, very steep, but I just want to show you the principle. So what we had here is water at a pressure of 500 kilopascals and a temperature of 20. Now there's a temperature of 100, so the temperature of 20, this is, as I've said, it's not according to a scale, so that would typically be the inlet point there. That would be point 1. Okay. Now it is going to end up at a pressure of 202. Okay, and the temperature at the outlet is going to be approximately 100 or a little bit more than 100. We've set 100.3. So there is 100. There is, let's say, there's about 100 there. So 101 would be typically there. So that would be 0.2 there. So, and I've got no justification for these entropy changes here. We know that there's going to be an increase in entropy because of the friction losses, but in principle, what is happening is that on the TS chart, we've got that in terms of the temperatures and the pressures. And fortunately, with the selection of this problem, we didn't move into the two-phase region, which would have complicated this problem. So with that, ladies and gentlemen, thank you very much. I would like to end this problem. Thank you.